All right, good morning, everyone. Welcome back to the second class. Today, what we're going to do is we're just going to get right into playing with some puzzles, in particular the SWAT puzzle. So I just want to remind you that from the course website, if we click on lectures, then there is the course book available. So download that, and we're going through it chapter by chapter. Today, we're going into chapter 1. Also, the puzzle boards. So this was the PDF that I wanted you to download and then cut out and be ready to play with. If you didn't manage to, if you don't have a printer for one thing, so you didn't manage to print it and cut it out, then that's no problem. For those who have printers, then certainly print and cut it out. But if you don't have one, you can certainly just use pencil and paper. You could even make your own cutout little squares and write numbers on them and then draw the rectangular box to sort of put the pieces in on a piece of paper, or at the very least, you could just redraw the box each and every time, or maybe just draw it once and then just erase and then rewrite the numbers in as you move them around. So there are all sorts of options that you can do if you didn't manage to create your own physical version of the puzzle beforehand. Okay, so what are we going to do? We're going to play around with the SWAT puzzle. This is not, it's not so much a fun puzzle in the sense that it's not marketed in any way, shape or form, but it is the template for which all of the other puzzles that we are going to study in this course are really built upon. And so getting getting familiar with this puzzle and just how pieces can move and kinds of questions that come up, it's a very good starter puzzle for generating those mathematical questions that we're going to be answering over the course of the term. So what does this entail? So let's just get right into the play. So I will bring mine onto the screen. So I've got my puzzle all laid out here. The idea with this puzzle, and you can follow along, is you've got these 8 tiles, and we are just going to mix them all up and then stick them back into the puzzle anywhere we want, onto the puzzle board anywhere we want. And the goal is to return every tile, every one of those blue tiles, back to its home location. And its home location is given by the number in the top left-hand corner of the box. So I immediately know that 1 is not in the right spot. 1 is currently in box 2, but I'd like 1 to end up in box 1. And similarly, tile 2 needs to be in box 2. Currently 6 is in box 3, it needs to be in box 6, and so on. So I've got to have to move these around. Now this is where the rules of the game come into play. What rules are we going to play by? Well, the rules we're going to allow to be flexible in that we will fix rules for a particular game and we will play with those rules. But then we might want to change the rules and see what other kinds of things can come up. So for us, we will start with the rule that, and here I'll just show it behind what's written on here, the rule or the legal moves that we're going to be using is that we will pick any 2 boxes we want and just swap their contents. So that is our basic legal move. And then pick another 2 boxes, swap the contents, pick another 2, swap the contents, and eventually, hopefully, if you can do it, you get all the tiles back into their original locations. So for us, I'll indicate this with the physical version. It's fine because I can just identify the 2 boxes I pick. Maybe I'll pick this one and this one. So those are the 2 boxes I'm going to pick, the 3 and the 6 box, and I will swap their contents. So I've swapped their contents, and now I'll just slide them back into place. And then continue doing this. Pick another 2 boxes. Maybe I'll do the box 3 and 4, and I'll swap their contents. And keep going until you get all the tiles back into their original spots. So go ahead and try that. Try a few puzzles. Just randomly lay them out. If you want to try some particular configurations. I've listed 4 here that you can try out and see if you can solve them. So puzzles 1 through 4 could be the ones that you want to try. Or you can do some random placement of the tiles and try to solve them. So go ahead and take a few minutes to just try that. Again, the goal is to use these rules. The rules are to pick any 2 boxes, swap the contents. The goal is to put the tiles all back into their original locations. Now, since I can't see you, so I don't know how people are progressing along, I'll ask for at various points for you just to pop a short answer into the chat window. So what we're going to do is we're going to keep track of some things. So I'm just going to label this first one. I'm going to rotate that word a little bit more just so I can fit some stuff in beside it. So we'll call this the swap puzzle or the swap game because the rule is swap 2 tiles in any 2 boxes. At which point I'm just going to say, you know, write the number in 1, 2, 3, or 4 of the puzzle that you've managed to solve. And you don't have to go in order. If you started with puzzle 4, then great. Okay, so it looks like someone's solved puzzle 1. We've got someone who solved puzzle 2. Oh, we've got some people who solved 1, 2, 3, and 4. So we've got some solutions here. Looks like 1's been solved. I like the 4. I like the fact that one of you, I lost it in the chat window, but one of you solved 4. That's always good because now if you're curious, you take a look at puzzle number 4. So that was William. It looks like, if I'm back up far enough. If you take a look at puzzle number 4, you can see, well, you're only 1 move away. You just have to swap the contents of 7 and 8. So this one is solved. Yeah, it looks like everyone's getting them. 1, 2, 3, 4. That one's solved. That one's solved. Okay, so if I continue on with my random arrangement just to get a feel for it, what I can do is I can start putting things back into their original place. So 1 will go into box 1, 2 will go into box 2. That's solved. I can say I want to solve box 3. So currently 3 is over here in box 7. So I will swap those 2. Now I want to put 4 in the right spot, so I can swap those 2. I can put 5 in the right spot, so I can swap these 2. I want 6 in the right spot, it is. I want 7, and I want 8 in the right spot. They're currently swapped, so I can swap those contents, and I get it solved. So we can systematically go through this and just say, I want to solve for box 1, solve box 2, solve box 3, solve box 4. So it might not be too surprising that no matter how we rearrange these tile pieces, it's always going to be solvable. And we could systematically go through and just solve 1 box at a time, starting with box 1 all the way through box 8. Okay, so that's what I mean by this puzzle doesn't seem to be that challenging, maybe not even that interesting, but let me just make a statement and see if you agree with this in the comments. So my statement is, based on the discussion we just had, no matter how I rearrange the tiles, I scramble them all up and I put them in some random places. No matter how I've rearranged them, can I solve this puzzle using that move or that rule of just swapping the contents of any 2 boxes at a time and just systematically swap, 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 swap? Do you see any reason why I couldn't solve this? Should I be able to solve this? Yeah, I think so, sure, yeah. Okay, so what's interesting about that is we have just discovered through play one of the most fundamental and yet powerful results about the theory of arrangements or permutations is that, yeah, I see that n minus one moves at worst. Very nice, yeah. So we've even can get some bounds on how many moves there are. Turns out we've got a fundamental result about arrangements or permutations is that every permutation or arrangement, I'm going to use those synonymously, but every permutation can be obtained, or if you want to think of it, restored to its proper order by just swapping two objects at a time. So if you have books on your shelf and they're out of order, you got maybe your Harry Potter series of books 1 through 7, and someone came in and put them out of order, you don't have to take them all off the shelf, dump them on the floor, and then sort them and put them back on the shelf. You can just swap them two at a time. Wherever book 1 is, swap its position with the object that, or the book that was in book 1's position, and so on. So this is actually a fundamental result about permutations, which we will prove using permutation theory, but we've already got a feeling for that this thing should be true, that we can rearrange objects by swapping two things at a time. I like that. Good comment, Brian. Adjacent swap is always solvable, I think. So yeah, and excellent. So Eric, you make a good point about there seems to be some sorting algorithm possibly at play here, insertion sort, or maybe even bubble sort, swapping two at a time. Absolutely. So there's a lot of rich mathematical and computing science theories that are sort of lurking in the background of this very simple game. So what we have is the idea that we can always fix any rearrangement, or we can always put things back in order by just swapping two at a time. And Brian, your comment about adjacent swaps, let's play that game. Let's say I've rearranged this and now I want to change the rule. No longer am I allowing you to swap the contents of any two boxes. I am only going to allow you to swap the contents of adjacent boxes. So only boxes that are next to each other. And we can sort of argue one fine detail. Would we consider 1 and 8 to be adjacent? Box 1 and box 8, are they adjacent? Some people say yes. Think of it sort of as a wraparound kind of thing, that 1 is adjacent to 2, 2 is adjacent to 3, and so on down, and 8 is adjacent back to 1 again, sort of a wrapping around effect. We could say that, or we could argue, and maybe in this context, no, we don't want to consider them adjacent. However you want to do that, that's your prerogative. You just build that into the rules of the game. Let's just, for sake of argument, say that they're not adjacent. We could make them adjacent, but we're making up the rules, so I'll just say, no, we're not going to assume they're adjacent. Okay, so now I want to solve this. What do I do? Well, I'm only allowed to swap adjacent things, so what I'll do is I'll take 1, and I want to get it all the way down here to the first position, so I'll just swap adjacent things like this. And this is sort of like what a bubble sort does. It sort of bubbles things up to one end. Here I'm bubbling them down to the bottom. Then I'll do 2. And then I'll do 3. Kind of like a leapfrog effect. And then 4. And I'm just doing adjacent ones every time. And 5. 6 is already there. 7 and 8 need to be swapped. And we're done. So not only do we have a fundamental result that says any permutation can be restored by swapping the contents of any two boxes, we actually have a further refined result that says we can do it without worrying about any two boxes, just we can restore them with swapping adjacent boxes. Okay, and so now what can we do? Well, now is where we start to continue this line of thinking and say, let's change the rules some more. So let's go to the next page where I start to change the rules slightly. So I'm going to call this variation 2. It's down at the bottom of the page there. I don't want to bring up the other variations just yet. Variation 2, let's play the same game, except now our legal move is we're only allowed to involve a swap of 2 boxes if one of those boxes is box 1. So it's box 1 and any other box, swap the contents. So every move has to involve box 1. Let's go ahead and play that game. Actually, I'll leave those up. So go ahead and work on those 4 puzzles again. And then same rules as before. Well, sorry, same rules. Same feedback as before. Once you've solved one, just pop it in the chat saying, 1 or 2 or 4, etc. Looks like we've got some solutions coming in here. Someone solved 2. Oh, sorry, someone solved 1 and someone solved 2. Someone's done 4. Someone's done all 4 of them. So 1, 2, 3, and 4. I'm just going to reset my tiles. All right, so let's have a look. Maybe we'll look at, I think this is puzzle number 1, 5, 4, 3, 2, 1. Yeah, looks like I've got them in the right order. So again, we have to involve box 1. So maybe what I'll do is I'll start with 7 and 8, and I'll swap box 1 and 2. Now 7's ready to go home. So I'll swap box 1 and 7. Let's get a little cluttered here, box 1 and 7. So 7's done. It's home. And then I'll swap boxes 1 and 2 again. And that puts 2 home. But now 8's back in box 1. That's where it started. But not to worry, what we've managed to do is we've managed to swap, or at least I should say put home 2 and 7. And now we've got 8 back here again. So I'm going to do the same thing. I'm going to try to put 3 home. So I'll bring 3 around here. And now I'm going to send 3 home. And now I'm going to send 6 home. And now 3 and 6 are home. And I'm going to do the same thing with 5 and 4. I'm going to send 4 home by first bringing it into box 1. And then from box 1, I'm going to send it to its home spot. And then 5 is going to go into its home spot, back to 8. 8 comes back to 1. And then everything's restored except 1 and 8, and I can swap those. And so we've managed to solve it. Now, there was sort of a lot going on there. It might not have been the same moves you used. So let's just look at puzzle 4 for a second. Puzzle 4 just had the 7 and the 8 swapped. And in our old version of the rules, the original swap version, we were able to just swap the contents of box 7 and 8 and solve the puzzle in one move. Now we have to involve box 1. So tile 1 is in box 1. It's going to have to move out of there. Unfortunately, that's where I want it to be, so I'm going to have to move it out of there and then eventually bring it back in order to get the puzzle solved. but that's not an issue. What I'm going to do is I'm going to involve it with one of the tiles I want to move. Then I can swap those two. And then I'll slide that one up. Now it's out of position, but that's no problem. Now I'll involve these two in the swap. That sends 8 home. And then I'll involve these two in the swap. And that sends 7 home. And then also, now 1 is back where it started. So how many moves was that to switch it in this rules? There was the 1 move that swapped these two, a second move that swapped these two, and a third move that swapped these two. So it now took 3 moves to just switch the contents of box 7 and 8 and 7 and 8. Okay, so we were able to solve it, but it wasn't as easy as it was with the original variation of the rules. Now we may ask, does it seem reasonable that any permutation can be solved in this way? So in other words, can I restore any permutation by using only swaps that involve box 1 and any other box? Playing with this a little bit, you might come up with the idea that, yeah, that seems reasonable. And again, this is going to be another fundamental result about permutations that we're going to prove. So what we're doing is we're playing, we're conjecturing, and these conjectures seem to be valid because just by sheer play, it looks like it's always going to be able to be solved using these moves. But after we conjecture, make a conjecture such that any permutation can be rearranged into its proper order by doing swaps with box 1, then we got to prove that. And we will prove these things. They'll come in later chapters, in like chapters 4, 5, and 6, and 7. But we're establishing through play the idea of building up at least questions that we have, maybe conjectures, so statements we believe to be true, and then we'll have to justify these later on. So this hits the heart of mathematics. Not many of your previous courses you've taken in mathematics probably hit the heart of mathematics in this way. This is how mathematics is developed. You play with stuff. In the case of like linear algebra, you play with vectors and you play with solutions to systems of equations, and you sort of try to figure out what has to be true of them. You make a conjecture and you try to prove it. But the play there is much different in the sense that it's playing with symbols on pages and moving them around and whatnot. They don't often represent physical objects to us. Whereas here in this course, all of our play is rooted on these physical puzzles, but we're still going through the mathematical process of conjecturing and then trying to prove our conjectures. Okay, so let's play with this a little bit more. I'm going to do another change to the rules. This is going to be variation 3. Now our rule is going to be pick any 3 boxes. So it's not 2 anymore. Pick 3 boxes and shift their contents either left or right. In other words, involve all none of the original 3 boxes, none of them have the original tile they started with. All the tiles had to move. So the only ways that that's going to happen is that they either all shift to the right, sort of in a circular motion, or they all shift to the left. So let's have a look at what this means. So for example, a legal move could be pick any 3 tiles you want and cycle them around. So I want all 3 to move, which means they're all going to move either like in this direction to the right, and then this one will come back around here, or there's another option in this case. Unlike the case where we just had 2 boxes and we swapped, here there's 2 options for how we can move them. Here we could shift them all to the left and then cycle them around and put them in their spots. So for example, I could take that one, and that one, and cycle them around. So 2 pushes over the 6 pushes over the 7 comes back, and it comes down. So we're going to call these things 3 cycles, because it's cycling 3 objects around, either to the left or the right. So with that in mind, with that new rule, we're not allowed to use the previous rule anymore. That's our only rule, cycling 3 boxes, contents of 3 boxes. Let's call that variation 3. I want you to go ahead and solve these puzzles, puzzles 1, 2, 3, and 4, and our usual criteria applies. Once you've solved a puzzle, pop it into the chat. Yeah, absolutely. A swap is just a 2 cycle. You got it. So we could say the original rules were we allowed to do 2 cycles. Now this new updated rule is we're only allowed to do 3 cycles. Okay, so we've got someone posting that they've managed to solve 3. Brian solved 3. Russ solved 1. It looks like we've got solutions for 1 and 3. Got some more votes for 1. That was more people who've solved 1. That's good. You can see it takes a little bit more thought now. So Jason, that's an interesting observation. So you're thinking puzzles 2 and 4 don't work or can't be solved. I want to ask a follow-up question to that. How far could you get with puzzle 2 if you were using this technique and you were trying to solve it? Let's say you tried to solve tile 1 and then tile 2 and so on. Yeah, so exactly. So it looks like, Jason, that you're able to take puzzle 2 and put it into the form of puzzle 4. So if puzzle 2 was solvable, then so would puzzle 4. And if puzzle 2 can't be solved, then so too puzzle 4 couldn't be solved, because you can always get from puzzle 2 to puzzle 4 or puzzle 4 to puzzle 2 by doing moves in reverse. So puzzle 2 and 4 are equivalent to each other in that you can get from one to the other. Ah, yeah. No, that's a good comment, Daniel. I know you look at puzzle 4 and you're like, there's only 2 pieces out of position. I might as well do that one first because it's probably going to be the easiest one. But in this one, it turns out to be quite challenging. So what was easy for the original version of the game, which was just swapping or 2 cycles, turns out to be hard in the 3 cycle version. And so I'm going to put, maybe question marks here. Because it doesn't seem that we're able to solve these ones. So, and you think it's probably because we're working with 3 cycles, so if 2 are off, we can't solve it? That's a good point. Maybe that might be the issue. I'm going to throw in another challenge, maybe puzzle number 5. And I'm just going to shrink this puzzle down for a second so that we don't have too many numbers to deal with. And let's make this our puzzle. So 1 and 2 and 4 and 3. Sorry, 1 and 2 and 3 and 4, each as a pair, had their content swapped. Can we solve this one using 3 cycles? Yeah, in this case, looks like we can do our first move is something like this. Sorry, maybe something like this. So now the contents are going to be 1, 4, 2, and 3. And then the next move is we can just shift these along. And that would solve it for us. So there'd be 2 moves we could do, and then we could solve it. 1, 2, 3, 4. So it looks like if there's 2 pairs that need to be swapped, we could do it using 3-cycle. And a lot of you are sort of pointing in the chat that a single pair to be swapped, that seems to be a problem with using 3 cycles. And it turns out that this is another fundamental result about permutations. And we will prove these things. Right now, again, we're playing and conjecturing. But we're going to prove these things eventually. We're going to prove these things from a rigorous standpoint using an algebraic theory of permutations that we will develop in this course. So we'll prove them beyond a shadow of doubt that it is impossible to solve 2 and 4. And the things that you're noting in the chat is that the impossibility is because you can really get down to just requiring, as a last step, the swap of 2 tiles, but that's impossible using 3 cycles. Okay, so here's the next observation I want to make. Because we may be able to look at puzzle 4 and go, well, I need to swap 2 tiles and I'm using 3 cycles. I just don't think that's going to cut it. Okay, but what about puzzle 2? If we were to just look at puzzle 2, could we detect that it wasn't solvable using 3 cycles without even doing any moves at all on it? So this is sort of coming up with a heightened sense of solvability or unsolvability of these things. In fact, what I'm going to do is I'm going to say, well, let's just return to the original swap game and see that if we play the original swap game on these puzzles, that something interesting happens there that is going to tell us that these pink question marks that cropped up are going to appear on those puzzles. Okay, so what do I mean by that? I mean, let's just go back to the original swap game. And some of you may have done this already, but I'm sure many of you didn't because it wasn't part of the instructions. Go and play the original swap game. So 2 cycles, swap the contents of any 2 boxes. But now count the number of moves you do. Count how many swaps it takes to restore the puzzle. And so I'll record some of those numbers here. So as you do it, just post the numbers in the chat. For puzzle 1, maybe use a comma notation, like 1, comma, and then the number of moves. Yeah, exactly. So you got it. Jason's already ahead of me here. Puzzle 1 took 4 moves so for his technique. So I'm going to list these numbers here. So it was done in 4 moves, and feel free to do it for the other ones as well. Okay, we've got some 4s and 7s for the first 2. So I'm gonna challenge you a little bit more. It looks like some of you are doing it. Well, all of you are coming up with the same numbers, which means you're all doing it in some sort of optimal way, which is fine, perfectly fine. That's a reasonable thing to do. Now just solve it without thinking about doing the best move at each stage. Just do a bunch of moves. They could be moves that help you or hinder you at the start, but just do a bunch of moves and then eventually hone down to a solution. So in other words, come up with a longer sequence of moves that maybe someone who wasn't thinking optimally would come up with. So for example, I'm going to go for puzzle 4, just to, these are, you never usually get these kinds of instructions. Do things in a bad way, right? Do things in a non-optimal way. But that's what I'm asking you to do. And the reason I'm asking you to do this is just for the purposes of exploration and play, to see if we can uncover something. So here I'm going to do that last example, and I'm going to do just swapping contents of any 2 boxes, and I'm going to do it in a way like this. Okay, so I'm going to swap the contents of these ones. So that's 1 move, 2 moves, 3 moves, 4 moves, 5 moves, 6 moves, 7 moves, 8 moves, 9 moves, 10 moves, 11 moves. Okay, so I did it in 11 moves. I will write that down. 1, 11. So that's what I'm kind of thinking. It's just give me various move sequences. You got it. Preet, you got it. Yeah. So Ampreet's observation is that if it took us an odd number of moves to solve it, then no matter how you solve it, it will always take an odd number of moves. So for example, puzzle 4 could be done in 1 move. That's odd. But I solved it in a completely ridiculous way, but it still took an odd number of moves. So there's a conjecture. So excellent. I like this. You guys are conjecturing now. So the possible number of moves is a multiple of the optimal number of moves. So that's an interesting conjecture. Let me go back to this version here and say that actually this one's a poor version because it's it's only 1 move away. So let's go to the one that was the last one there, 8. Sorry, I'm going to go to puzzle 2 because that one's easier for me to set up just by shifting things down. Okay, so puzzle 2. So it took 7 moves to do it. What we could do is this. So I'm going to solve it in the 7 moves. Well, I'll just solve it. It'll take me 7 moves just because I'm bumping things along. But then I'll do something near the end. So how many have I done? 1, 2, 3, 4, 5 moves, 6 moves. And then I'm going to do this. I'm going to swap them, 7 moves, and then swap them back, 8 moves, and then swap them back again, 9 moves. So I did it in 9 moves. My last 2 moves didn't really make sense because I messed it up again and solved it. But the point is that whenever I've got a solution, I can always do 2 extra moves. So 1 and then swap them back, and always bump up my number of moves by 2 and still have a solution because I just swap back. So I can always add 2 extra moves or an even number of moves and still have a solution. So this explains why if I had a solution using 7, I could also get one that involved 9 or 11 moves or 13 moves. I just keep doing the ridiculous thing of swap 2, swap them back. So I insert 2 extra moves that really undo each other. Okay, so here's the interesting thing. What do we notice about, now we know that this 4 could have been a 6 or an 8 or a 10. It could have been any number of even moves of bigger than 4 we could have done it in. And variation 3 using 3 cycles turned out to be solvable. This one took an odd number of moves to solve, and we weren't able to do it using 3 cycles. This one took an even number of moves to solve, and we were able to do it using 3 cycles. This one took an odd number of moves to solve, and we weren't able to do it using 3 cycles. So there seems to be something deeper at play here, that the number of moves, or the parity of the number of moves, so whether it's odd or even, of solving the puzzle using our original rules of just swapping 2 at a time, can give us insight as to the solvability of the puzzle when we change the rules and make it 3 cycles that we're using. And so this is known as the parity theorem, if you want to think of it as a theorem. We'll get to a formalization and a proof of this, but this is known as the parity theorem in the theory of permutations or the theory of arrangements. And that the parity theorem really says that if it takes an even number of moves to solve, then it will always take an even number of moves, and vice versa. If it takes an odd number of moves to solve, it'll always take an odd number of moves. And so if we think about that, if it takes an even number, it'll always be an even number in terms of swaps. Or if it takes an odd number of swaps, it'll always be an odd number. Now let's think about the 3 cycle. 1, 2, 3. 1, 2, 3. So let's, again, I shrunk my board down, so just focus our attention on these 3 tiles. If I was to play this game of let's do the swap rules on this, swapping the contents of any 2 boxes, how many moves does it take to solve? Is it an even number of moves or an odd number of moves? Oh, I'm glad you're finding it interesting, Jason. That's a good comment. Thank you very much. Yes, that's the idea, is we want to play, explore, conjecture. So how many moves? Even, even, even? Yeah, it's going to be an even number, because the first thing I'm going to do is I'm going to swap these 2. That's 1 move. So that moves the tile 1 there and the 3 there. And then I will swap these 2, and that solves it. So to get from there to there are 2 swaps required. So that means a 3 cycle is equivalent to doing 2 swaps. And so if I, and this comes back to this conjecture that we developed that says, if a 3 cycle is equivalent to doing 2 swaps, then to solve a 3 cycle means that you would have to do 2 swaps in the optimal way, or you would have to at least do an even number of swaps, because it takes 2 swaps to solve it, and other solutions will always be the same parity as that optimal one. And so there will always be an even number of swaps required to solve a 3 cycle. And so 3 cycles will always be equivalent to doing an even number of swaps. And then that comes back to the observation that was made in the chat that, but this is only 1 swap that we need to do to solve the puzzle. That's an odd number of swaps. So I can't solve it. It's an odd number of swaps, but 3 cycles are equivalent to doing even numbers of swaps. So there's a parity issue at play, an odd and evenness. And so what we've done, interestingly enough, in this course so far, is, let's call this day 1, because last day was more of a overview of policies and procedures and the like. So let's say day 1 of the course, we have established 2 of the most fundamental and important results about permutations. And those are that every permutation can be restored by swapping 2 things at a time, and every permutation falls into one of 2 categories. It's either an even permutation, in that it takes an even number of swaps to fix it, to put it right, or it's an odd permutation. It takes an odd number of swaps to put it right. Those 2 results about permutations are so fundamental and so important that they're often these things that don't appear in, if you do a group theory course, so the 300 level math course situated around the theory of groups and the abstract theory. These are often not proved for quite a number of weeks in the course. But we've discovered them. We've discovered them through pure play, and now we have a feeling that why these things should be true. We're still going to go ahead and prove them. We're going to put them on firm foundation and prove these results. But we've made them our own. We now at the core of ourselves know that these results should be true just by playing with these ideas. And then now we'll go ahead and develop the theory of permutations to prove them. But that's the power of doing this play, is that we get to experience mathematics from a tactile point of view, and we get to make conjectures, things that seem reasonably true, and then now we're left with the idea of proving them. Okay, just to wrap up today, there's the notebook, the textbook, I should say, has some more variations that you can play with. What about swapping pairs? What about doing swaps of pairs inner and outer for 4 consecutive boxes? What about picking any 4 boxes and shifting the contents right or left? In other words, 4 cycles. You can play the game with these and come up with similar ideas for when things should be solvable or not. And this is going to be things that we do throughout the course and uncover. The thing to realize now is that the 15 puzzle is really just a version of this swap puzzle. And I'll show you why that is. Because the 15 puzzle, it's really about just dumping tiles into, in this case, it's a 4x4 grid. But the idea is we're still trying to swap pieces. The home positions are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And then we just call this box here the 16th box, which I'll drag over here. We call this box here the 16 box, which these don't have the numbers like they do on the one I've just drawn. These numbers in the top left corner indicate the box number, which piece should go there. And then what we do is we just slide pieces around. And we can think of this sliding as just swapping the contents of the box with the empty tile and the box next to it that has a number tile. So I'm swapping the contents of these two boxes when I do that. I swap the contents of these two boxes when I do that. So this puzzle is really just a swap puzzle in a different form. It's a rectangular form and the rules are still sort of applying. All of these puzzles that we're going to deal with are really swap puzzles like this. Here we've got 20 numbers. There's a home position for them. And we're able to shift contents around in the circle. That's one of our rules. The other one is we can turn the turntable and swap these two and these two. So those are our rules in this case. So all of these puzzles are really just the swap puzzle in disguise. Now, the Rubik's Cube is as well, so is Hungarian rings. The Rubik's Cube, we can think of just numbering the stickers as we do a rotation. The stickers are really our tiles now in this case. They move to new locations of where stickers were, and then those numbers are just sort of jumping from box to box. The boxes now we're thinking of sort of this fictitious sort of layer of skin that's around the Rubik's Cube, and they're sort of sliding, a tile is sliding from one location to another one. And so we're thinking of these numbers as not only on the tiles themselves, but on this sort of box that the tile lands in. But again, just a swap with now many more numbers, so 48 numbers, and some complicated rules for how tiles can move around, which is just equivalent to rotating a face, but a swap puzzle nonetheless with various rules. I do have a table here of puzzle moves names for the Rubik's Cube. That's in the book. We'll be using these from time to time just to talk about what move we did on the Rubik's Cube, but I won't bother mentioning those in class just yet. So that brings us to what are permutation puzzles? What are these things that we're going to be studying in this course? It's really just the swap puzzle where the number of boxes and the number of tiles are arbitrary depending on which puzzle you're looking at. Could be 8 like the swap puzzle we were looking at, or it could be 48 like the Rubik's Cube, or it could be 20 like the Ovotrack, or it could be 16 like the 15 puzzle. But there's also a set of rules for moving those pieces. So what is a permutation puzzle? First of all, it's a one-person game. You only play it by yourself. There are finitely many moves at each stage. So once you're at a stage of the puzzle, there's only finitely many things you can do. There's a finite sequence of moves that solves the puzzle. There are no chance moves or random moves. You don't roll a die or anything like that. And there's complete information about every move that you have. You know the state you're currently staring at, and you know what happens when you do each of the moves. So you have all information you need. Each move only depends on the present position. So there's no moves that are restricted because of how the puzzle's currently sitting. That's what a one-person game is. A permutation puzzle is just a one-person game, so it has all those previous bits of information, with the additional feature that it consists of a set of objects, 1 to n, and those both represent the tiles and the boxes. And so every move is just a permutation of those tiles amongst the boxes. Every move is invertible. If you do the move, you can always undo it. You can do the reverse of it to get back to where you were before you did the move. And additionally, the last step is that if you do a move and do another move, then the resulting configuration is really just obtained as a product of the two move sequences themselves. So there's a multiplication at play here what that multiplication is and whatnot is still something we have to discover, which we will. But that's the idea of a permutation puzzle. And that's what the content of this course is, studying permutation puzzles and the mathematics involved in really coming up with a complete understanding. All right, so that's it for today. I will just stop the recording.